All right, welcome to the Blueprint Room. I am your chief architect for today's session, and we are laying down the ultimate, unshakable blueprint for tackling AS and A-level quadratics. In this explainer, we are not just looking at math problems, we are treating your Cambridge Mathematics 9709 exam answers exactly like load-bearing, high-rise skyscrapers. You see, most students walk into the exam hall treating their answers like mere ink on paper. They just throw numbers at the page and hope something sticks. But an elite structural exam engineer, they know that every single equation, every justification, and every logical step is a steel beam holding up their final grade. Today, we are going to look at exactly what it takes to survive the extreme pressure of the examiner's red pen. We are going to establish your core foundation, erect load-bearing analytical arguments, and construct structural sentence connections that will absolutely survive rigorous examiner stress testing. So put your hard hats on, get your drafting tools ready, and let's get to work on this construction site.
Now look at this. This is our foundational challenge, straight from the city inspector, the senior examiner themselves. They've issued a direct, very clear warning. Quote, examiners report that quadratics, specifically solving quadratic equations and inequalities, is one of the most misunderstood areas in mathematics. Let that sink in for a second. Quadratics. It seems so basic, right? You probably learned the quadratic formula years ago. But the examiners are telling us that at the AS and A level, this is where structures fail. This is the exact point where buildings collapse. You absolutely cannot construct a high-scoring paper if you are building on a swamp of misunderstood concepts. If your core understanding of how to solve an inequality is flawed, everything you build on top of it, the calculus, the mechanics, the advanced modeling, it all comes crashing down. So we are fixing this massive foundational vulnerability right now. We are going to isolate the exact building regulations and the specific assessment objectives that the Cambridge examiners strictly enforce.
Here is our master blueprint for today's structural upgrade. Step 1, laying the quadratic foundation. Step 2, the structural methodology. Step 3, the method mark safety net. Step 4, surviving those examiner stress tests. And finally, Step 5, advanced architectural evaluation.
Let's start with phase 1, laying the foundation and establishing the core principles.
To build high, to really reach those penthouse-level grades, your answers have to target 3 distinct cognitive domains of assessment. These are your mandatory building regulations. We have knowledge and understanding, application, and analysis. Think of knowledge and understanding as your raw cement. This is the raw material. The formulas, the discriminant, the basic structure of the quadratic equation itself. If you don't have cement, you don't have a building. But cement alone is just a puddle on the floor. That brings us to application. Application is the heavy steel rebar you place inside that cement. It's how you take that raw formula and actually apply it to the specific unique dimensions of the problem in front of you. It's shaping the material to fit the site. And finally, analysis. This is the actual structural engineering mathematics. This is where you evaluate why a specific root is mathematically valid, or why a certain range of values perfectly satisfies the quadratic inequality while another range causes a critical failure. You need all 3 of these materials perfectly mixed and integrated. If you just have knowledge, your building is brittle. If you just have application without analysis, you have no structural integrity.
The examiners explicitly emphasize that a strong foundation means your conceptual understanding has to survive even when they throw an unfamiliar, highly complex mathematical context your way. They want to see connected, conceptual understanding that is fully transferable. Now, I see this fail on site all the time. Take 2 junior builders I had at the drafting board just this morning, Alex and Sam. Alex, bless him, he's a hard worker, but he just stacks up heavy bricks of raw facts. He memorizes every formula, every identity, and he just dumps them onto the exam paper without checking if the steel frame can actually support the weight of that logic. He builds a purely descriptive structure. Then you have Sam. Sam wants to put up all these shiny glass panels and decorative features. Sam uses all the fancy mathematical terminology, jumping straight to complex modeling, but completely forgets to cement the foundational columns first. Both of their buildings collapse instantly under the weight of the mark scheme criteria. Top-performing students don't just memorize formulas like Alex, and they don't just use buzzwords like Sam. They understand the connected, conceptual logic behind the math so they can adapt when the blueprint suddenly changes.
Moving into phase 2, the structural methodology. It is time to erect the steel frame. You absolutely cannot just dump numbers onto the page like a pile of raw bricks and expect the examiner to build the house for you. You have to secure your structure using mandatory procedural conventions. We're talking proper headings, correct terminology, appropriate formats, and clear, undeniable annotation.
When the examiner looks at your paper, they should see a perfectly drafted blueprint. They need to trace your logic from the ground floor all the way to the roof. If you're missing clear annotations, it's like leaving an open elevator shaft in the middle of your building. It's a hazard. The examiner gets lost, the logic breaks, and your marks plummet. You have to use the exact correct terminology to label your load-bearing walls. So how do we enforce this? By using a standardized sequence. Let's go back to Alex and Sam at the drafting board. They were having a massive ironwork peer debate about how to frame a high-tariff past paper paragraph. Alex wanted to fill the whole paragraph with a massive cement block of terminology definitions. He's saying, let's just define the discriminant, define the roots, and move on. But Sam rightly argued, no, Alex, without a hollow space for a dynamic analytical breakdown, without testing the conditions of the inequality, our structure has zero flexibility to hit the top band scores. And Sam hit the nail on the head. You need a process. Step 1, identify key elements. Pinpoint those exact quadratic coefficients from the raw data. Step 2, apply relevant principles. Set up the inequality correctly and map the curve. Step 3, execute analysis with clear working. Step 4, verify your results. Run a stress test on your critical values. And step 5, present in the appropriate format. State the final range clearly. When Alex and Sam rewrote their skeleton using these exact 5 steps, their argument went from a pile of rubble to a perfectly engineered load-bearing response block. Every mathematical beam was perfectly aligned. All right, let's look at section 3, the method mark safety net. Because let's be real, what happens when a final calculation fails mid-build? This right here is your literal physical safety harness, the method mark strategy, the practice of earning marks for the procedural process and showing you're working, even if the final calculated result is totally 100% incorrect. The Cambridge Examiner reports are incredibly clear on this, and honestly, it drives me crazy how many students ignore it. Students lose massive amounts of marks by simply not showing they're working. Imagine building a 20-story building, making one tiny error on the blueprints for the roof, and the city inspector bulldozes the entire building. That's what happens when you don't show you're working. If you drop a negative sign on line 2, your final answer on line 10 will be wrong. But if you wrote out your structural methodology step by step, the examiner can see the scaffolding. They can say, the math logic was perfectly sound, they just dropped a brick on the top floor. Those method marks can completely save your entire grade. Always, always show your scaffolding. Okay, hold on. We are hitting an unexpected structural roadblock. I need everyone to pause the blueprint animation. Site inspection. Before we pour the final layer of text concrete and secure this high-scoring paragraph framework, make sure your construction line is fully reinforced. Subscribe to Ace the Exams, that is at Ace the Exams, right now, and turn on all notifications to receive our weekly structural grade upgrades. Whether you are building a foundational IGCSE base or setting up a towering A-level skyscraper, this channel is your primary grid. So lock it in, hear that metallic click of the hard hat, and let's get back to the build. We're going to apply the Peel methodology, point, evidence, evaluation, link, to rivet your mathematical data straight into your core thesis column. Phase 4, surviving the examiner's stress tests. Let's review the top structural failures that cause these answers to collapse under pressure. Stress point number 1. The absolute biggest stress fracture identified by examiners is when students confuse cause and effect in quadratics. This completely misaligns your logical framework. For example, when you are solving quadratic inequalities, what do most students do? They find the critical values, which is great, but then they blindly guess the inequality signs without actually understanding the physical geometry of the parabola. They confuse the effect, the final numerical range, with the cause, whether the physical curve on the graph dips below or rises above the x-axis. If you don't mentally or physically map the cause to the effect, your structural beams aren't actually connected. They are just floating in midair. And the second the examiner applies pressure, your score is demolished. Vulnerability number 2. Forgetting to check the requested format. This is the equivalent of installing shiny glass panels before cementing the main columns. The blueprint asks for the exact form, like a fraction or a surd. And what do? You punch it into the calculator and provide a rounded decimal. You have just violated the examiner's strict building codes. Without the proper presentation and requested terminology, the examiners simply cannot safely navigate your logic, and they will red tag your site. And point of failure number 3, providing answers that are not specific to the given context. Listen, your building must fit the exact physical environment it was requested for. Let's say a quadratic equation models the height of a physical object thrown into the air over time. You run the quadratic formula, and one of your mathematical roots comes out to -3 seconds. You cannot just box that answer, write it on the line, and walk away. A negative time value in this specific real-world context is structurally impossible. It is an invalid route. If you don't explicitly evaluate it and reject it based on the context, you are telling the examiner you have no idea what the numbers actually mean in reality. Section 5. Advanced Architectural Evaluation. We have laid the foundation, we built the frame, now we are building the penthouse to secure those top band scores.
Let's look at this comparison on the drafting screen, a basic descriptive framework versus an analytical and evaluative framework. A descriptive framework leaves you stuck on the lower floors. You are merely describing what a quadratic is or narrating the steps you took without explaining why. But an analytical and evaluative framework, that unlocks the absolute highest marks. If a complex question presents a set of roots and asks you to evaluate a mathematical model, you must extract the core metrics. You have to analyze why one modeling approach is mathematically superior to the alternative in this specific context.
It's time for an interactive viewer rebar stress test. I want you to imagine a complex source data chart flashing on a 60-second visual countdown timer. To construct a load-bearing evaluative argument before the clock runs out, you have to actively compare the approaches. You have to identify the similarities and the differences between the mathematical models. You have to use comparative connectives to bridge your paragraphs. You absolutely must support your comparisons with hard, calculated evidence. And crucially, you have to identify the limitations and assumptions you made when modeling that quadratic. Did you assume air resistance was negligible? State it. Expose the limitations and rivet your conclusions together with undeniable structural proof. That is how you extract the single most high-yielding core metric needed for construction.
So, we have inspected the core principles. We have erected a strict procedural steel frame. We've bolted on our method-mark safety nets. And we've walked through the top 3 points of failure. Before you step onto the final exam site, you need to ask yourself one question. Is your quadratic structure built to withstand the examiner's ultimate stress test? Are you just blindly stacking bricks and memorizing the shape of a parabola? Or do you truly fundamentally understand the hidden architecture of the mathematics beneath it? Keep practicing these past paper blueprints. Always secure your method marks and rigorously test your own foundations. See you on the next site built.